Thank you all for coming. I'm Kevin Jaffe, faculty member in computer science, and it is truly my honor to introduce today's speaker, Dr. Fred Brooks. Dr. Brooks told me in introducing him, keep it dead short. And if one thing you need to know about Dr. Brooks is you should always take his advice. So I will, but I will just give you the barest highlights of his background. He holds a PhD from Harvard. He had a brilliant and distinguished career in industry. He founded the computer science department here, had a brilliant and distinguished career here at UNC, and I think has more accomplishments than I could read off in 20 minutes, but I think that's going to come out in his talk as he tells us about a personal history of computing. So without more ado, let me introduce Dr. Brooks to give today's lecture.
The first programmable computer was designed by Charles Babbage in the 1830s. Babbage was Astronomer Royal. He was responsible for making navigation tables, and they were all done by hand, and they were full of mistakes. And he decided an automatic machine would be able to make them without mistakes, and he designed one that even printed automatically, made the plates from which the tables were going to be printed. Now, unfortunately, his grant ran out, and he wasn't able to get his machine to work. But two copies have been made more recently in our lifetime, and they in fact work. Now, Babbage's was the first programmable machine, and the programming has always been an interesting characteristic of computers. And so his machine used a Jacquard loom endless belt of cards. Each card controlled the needles to make one row of textile, embroidery or whatever you wanted to make, and each needle controlled one thread in that. So he used the needles to control the valves, essentially the gates, and in his machine. As I say, he didn't get it to work, but he had the right idea, and he conceived of the programmable computer. Now, scientific computing before 1940 was done with slide rules, tables of functions, thick tables, and mechanical calculators. Now, don't sneer. The atomic bomb was designed with these. The airplanes, even the C-130 that's flying today, was designed with this technology. And so scientific computing was well advanced before there were computers. The first automatic computer that worked was developed by Konrad Zuse in Germany behind Hitler's curtain, so we didn't know about it. It, like Babbage's machine, it was programmed with an endless set of punched holes, in that case, in film. I had a chance to meet Konrad Zuse once, but at an occasion in Switzerland, but we didn't share a common language, so we exchanged pleasantries through an interpreter. He was very, very dignified, and it was a great pleasure, great for me to meet this real pioneer. The other real pioneer that I got to know very well indeed was Howard Aiken. And it was Howard Aiken's design of an automatic computer programmed with a punched paper tape, like Babbage's essential machine. And Aiken peddled his design around to various calculator manufacturers and persuaded IBM to build it. They had a rotating wheel technology they used in accounting machines, electrically clutched, and so the holes in the punch card controlled the wheels would do add or subtract, and there was a multiplier. And so Aiken's was the first American computer. It was announced in 1944. I was 13 years old, and I read about it in Time magazine. And I had been interested in manual business machine methods. And so that turned me on, and I decided then that computers were what I wanted to do. So you couldn't study computer science when I went to college. There wasn't any. So I studied physics, but to graduate school, I went to Harvard, where Aiken was still teaching, and Aiken became my thesis advisor. So along with several other people here, Bill Wright was in that team, Peter Kallinger was in that lab, and we got to know Aiken very well indeed. Aiken was the architect of that machine, and it's important, I think, to distinguish in computers the architect who sets the specifications and how it appears to the programmer, the implementer who decides what the logical construction is, and the realizer who decides what the technology realization will be. And so the Harvard IBM Mark I, Aiken was the architect, IBM engineers, Bryce, Lake, Durfee, and Hamilton did the implementation, and they already had the rotating wheel technology that they were able to build it from. Now, the computer had the longest word length ever built. It had 23 decimal digits, and as a consequence, when I was a graduate student in the 50s, it was still running because there were jobs, especially orbital calculations, in which error accumulates, in which the 23-digit precision was worth compensating for the fact that it did 3 operations a second. Here was Aiken as the Navy commander in charge of the laboratory that built and put in place not only the Mark I, but the Mark II, the Mark III, the Mark IV. The Mark II was a relay machine, the Mark III a drum machine, the Mark IV a vacuum tube machine with a drum for the main storage. And Aiken was a very forceful character. But look at the Harvard Mark I. This was 55 feet long, powered by a rotating shaft that ran the whole length and turned the little wheels that turned the little wheels this way, that turned the little wheels this way. And you can't see the punch card thing in the back, but it was an endless loop of paper tape, maybe 20, 30 feet long, depending on the length of the program. Aiken, as I knew him, looked like this, and if you look at the 2 pictures, you look at those Spockian ears and those fierce eyebrows. He stood tall, and when he looked down at you and was mad, you looked like you thought you were looking at the devil. We called him the boss. He had been called the commander when it was a Navy operation. We called him the boss. Everybody never called him anything but the boss. He was a person of very strong will. He was also a person of great vision and originality. He, among the pioneers, clearly saw that the principal application was going to be business and not scientific computing. So all the earlier machines that people had been worked on were aimed at doing scientific computing. So his vision was clear, and he assigned several of us to do PhDs on business applications of computers. He thought, and I think he was mistaken, I think I proved he was mistaken in my dissertation, that you could save a lot of money by specializing a digital computer for one application. And that turned out, I think, not to be the case. The team had quite a spirit. So every day at 5 o'clock, we gathered in the machine room with the Mark I on one side and the Mark IV on the other side for coffee and conversation. The conversations were always interesting. If Aiken was in town, there we were. He loved to have an argument. If you pushed back, he respected you. If you didn't push back, he would run over you. He ran over you. Surprisingly enough, he was a super dissertation advisor. He gave a great deal of freedom in which way to go. And he came to the office every day and wanted to see the new prose. Guess what? There was new prose every day. And so most of us finished in 3 years. So there's an example for those of you who are thesis advisors. He recognized then that the big market was going to be what today we call big data. And so these were applications that as early as the 1900s were already being done by first manual methods and then by punch card methods. And some of them were quite surprising. Payroll is obvious. Utility billing is obvious. Railroad car accounting is not obvious. It turns out that the railroads pay each other for every day one of them's car is on another one's line, and you have to keep track of which car is on which line every day and send the bills back and forth. A big accounting job. The decennial census was the occasion for the invention of punch card machines. Now, most of the ones on this list can be done in a batch fashion. It turns out that the inventory problems, whether it's Air Force seat inventory or whether it's wholesale drug inventory or hardware, can't be done that way. You have to have a real-time system that will change, and credit card accounting, that will change the inventory, and credit card accounting is an inventory problem, minute by minute to stay up to date. And it turns out that required another whole kind of development of computers. Now, let me back up. Okay, I missed one, I think. Hollerith was in charge of the census, and the 1880 census near about didn't make it to the 1890. And so it was very clear that with the population going up, that the 1890 census wasn't going to get there before 2000, before 1900. And so he set about to figure out how to do that. And this is his first punch card machine. On the left, you'll see on the counter, you can barely see it, the manual key punch. On the right, you can see the manual reader. It's a set of pins that comes down like this, sensing all the holes in the card at once. And the dials, the 45 dials, each one reflects one pin. So when the thing comes down on a card, all the dials tick up that are punched, for which the holes are punched. Now, here's the nice thing. There's a sorter. How does the sorter work? You set it to which hole you want to sort, and it opens that pocket and none other. So then you drop the card in, so the cards are transported, the hard part, manually, but the logic to make sure they get in the right hole is done automatically by the pin sensing. So Hollerith had that neat under control. Well, the punch card system that was put in place in 1890 evolved, and so by 1950, punch card machines were the way the big data problems were done. Now, several people were trying to build automatic computers after Aiken. But there came a crucial paper by Birks, Goldstein, and von Neumann in 1946, an outgrowth of the work done at the University of Pennsylvania by Aiken and Malkley, that said the way to build computers is to store the instructions and the data in the same memory. Now that turned out to be a real breakthrough, because that meant as one went from one problem to the next problem. You could change how much of your limited memory was used for data and how much of your limited memory was used for instructions. Later we learned that if you do that, then when you change your data, you can mess up your instructions. And so in the Stretch computer and later computers, we put in memory protection that re-separated them again, but still left the flexible boundaries that enabled the allocation. The Birks, Goldstein, and von Neumann paper is the most important computer paper ever written, and if you've never read it, you ought to go back and read it. You will be astounded at how much of what we understand today was done in that very first paper. Sir Maurice Wilkes, who built the first stored program computer that was useful, says, "I sat up late into the night reading the paper. And from that time on, I never had any doubt as to which way computer development would go." Wilkes says, now, we talk about the concept of the machine set forth there as a von Neumann machine. Wilkes is very careful to say, and I've heard him say several times, don't give von Neumann all the credit. The work really came out of the University of Pennsylvania predecessor. Now, Atanasoff got the patent for the first computer, and most of us who are in the computer field and understand the issues feel like the judge did not, and that was just plain wrong. The other most important paper for you to read is Vannevar Bush's PEMEX. I'm not going to talk about the web and how it's searched, but this 1945 paper is the other one that will astound you with the concept of the web as we see it today and the ability to follow trails along in exactly the way we do today. The first computer that was useful was the Cambridge EDSAC, built by Wilkes and put in service in 1949. Wilkes had gone to the Moore School lectures at Pennsylvania. He had gone home and he wanted to make one because he was in charge of the computing center for the whole Cambridge scientific community. And the computing center consisted of a whole lot of girls working desk calculators, and like 40 or 50 of them, solving problems for the various engineering and scientific departments. He had worked on radar in the war, and so he undertook very conservative engineering. His machine, you see, it was 650 instructions a second for an electronic machine. He used memory delay lines that were ultra reliable, but it was the first stored program computer to really do real work. Here's a picture of the EDSAC. As you can see, vacuum tubes all over the place with Wilkes standing in the white coat. I did 3 sabbaticals at the invitation of Wilkes in his laboratory, and so we had a chance to talk starting in 75, and then the last one was after 2000. His contributions to computing were probably more different contributions than any other of the computer scientists. The EDSAC, they wrote the first book on programming. They invented symbolic labels. They invented subroutine libraries. His colleague David Wheeler invented the subroutine in macros. Then Wilkes published another whole paper, said the one best way to implement computers is with microprogramming. And you can agree or disagree with that, but it was fundamental at the time. And then he invented cache memories. And so his contributions, and he then built an early time sharing system and a ring client server system. He won the first Turing Award and founded the British Computer Society. When I was visiting with him in the 2000s, he was 94. He was sharp as a tack. I went back and read his 50-year-old papers, and it was incredible how accurate his technical judgment and predictions as to which way things were going to go were. He was having physical trouble. He walked with a cane, and most of his friends had died, so he came into the lab every Thursday, and he was eager to talk old times, so we talked old times a whole lot. But the most memorable thing he said, well, one thing he said in the 80s, he was walking me through the St. John's College faculty garden, of which he was very proud. And it had been announced in January that he was to be knighted. And so I asked him, I said, Morris, when do you go to Buckingham Palace? In the very British fashion, he said, on that subject, I have received no command. On my third stay there, he said, Fred, when you're in your 70s, you just keep on keeping on. When you're in the 80s, you just keep on keeping on. But Fred, he said, the 90s are different. And I thought, God grant. His colleague, David Wheeler, as I say, was one of the co-authors of that first programming book. He invented a fast Fourier transform that was acknowledged in Martin Ryle's Nobel lecture as indispensable for making synthetic aperture radio astronomy. He built the first operating system. It was all of 31 instructions. And he was a very sweet person. The first commercially delivered machine was the Univac 1. And this was 1941, so this is two years later than the machine. We had one of these installed in the Harvard laboratory some years later. It used delay lines, once again, for storage. It was a decimal machine, and Eckert and Malkley at Pennsylvania had come up with it. They were better engineers than businessmen, and they went bankrupt, and so Univac, Remington Rand bought them. But the Univac, then, it was the first commercially available machine. It was designed for the big data problem, the file maintenance problem. So it was magnetic tape, there was no punch card reader or punch attached, but you did things offline with tape. It had 1,000-word memory, and it did 2,000 operations a second. So way more than Wilkes 650. And it used 120 kVA of electricity. Okay, so because to keep the delay lines at uniform speed, they had to be heated. So the whole thing was one big tank in which the memory was kept warm. They sold 46 copies of it, and here Aiken and Malkley, after they lost their patent fight to Tanasoff, and everybody knew it was an unfair loss, John Malkley was kind of embittered to the end. I remember having lunch with him at one point, and it was just sad that considering how crucial that contribution had been, the fact that the lack of recognition in the patent hurt his spirit. Was very sad. Press Eckert, on the other hand, just brushed it off and went on. In the early days of computing, conferences were cheap. And one of the ways they were cheap is they would put 2 conference delegates in a hotel room, and this was done somewhat arbitrarily. So I got put in a hotel room with Press Eckert, even though he was working for Univac and I was working for IBM. But I got to know Press, and he very impressive engineer. Malkley was the architect. He was a mathematician. Eckert was, in fact, an electrical engineer. Now, the machine that I learned on, and I think Bill Wright learned on, was the IBM 701. It was IBM's late entry into the computer business. The Univac had gotten to be known as everybody's computer because it was used to predict the outcome of the 52 election, and that was a successful prediction. So then IBM got into the business at John Watson Jr.'s pressing his daddy to, this is going to be important for data processing. And so Watson Sr. authorized the manufacture of 18 computers for the Korean War effort. So it was called the Defense Calculator. It was used like the Manchester machines that used the vacuum cathode ray tube memory. It had 4,000 half words, 2,000 words of memory, and a 12 microsecond memory cycle. Here's a picture of it. If you look at this is interesting because from the beginning, the IBM computers had to be made so they could fit through doors and in elevators. And so this one folded shut to do that. The machine, Bill and I both used at North American Aviation in the summer of 54. And it had a mean free error time of about 10 minutes because the cathode ray tube memory lost bits freely. And so therefore, it had a magnetic drum backing store. And so every 5 minutes, you dump the whole memory out on the drum. And then when the machine failed, you'd reload the memory and then restart and restart from there. Well, clearly this was untenable. And so IBM went on to pick up the core memory that it invented at MIT and RCA. And in the 704, a couple of years later, came out with this machine that had the core memory and was very reliable. It also had the first commercial floating point. Now, Zuse had floating point in his machine. His machine was made of sheet metal gates and sheet metal memory with punch film programming, but it was a binary machine with floating point in it. The 704 also introduced index registers, which had been invented at Manchester, and this was the first commercial copy, and it became kind of the standard scientific computer, vacuum tubes. And as I say, it was very reliable. So then, meanwhile, Univac had bought Univac Scientific, a group of Navy machine builders who had been built code-breaking machines, and they had a competitive scientific line. And the two went head to head. And I think that's an important lesson as to why the 704 beat the 1105 competitively. The 1105 was faster. It had an 8 microsecond memory, not 12. It had two address instructions, not one address instruction. So each address was more powerful. but it was tape only. And so you put your cards into a card-to-tape converter. You took the tape over to the machine and mounted it. You ran your problem, and then you took your tape with the answer on it back to a tape-to-printer machine and mounted it and printed off your results. Whereas the 704 had directly attached card reader and printer. My recollection, and I would be interested in Bill's, is that the characteristic was that when your last card of your program disappeared into the reader, the printer started burping almost immediately, dumping your memory for where you'd made a mistake, a bug. And what was the difference? The difference is the 1105 was designed for production. 704 system also would do quick turnaround for debugging. And as Wilkes had said early on, I learned
canonical
I was going to spend the rest of my life.
canonical 폼이 뭔지 까먹어.
Now, the 704, also the Univac had floating point optional and had index registers optional. 704 had a mandatory. If you bought the machine, you paid for these features. But this meant that since every customer had these features, John Backus, in developing Fortran, could count on having them. And that turned out to be crucial for making the Fortran compiler. So Backus introduced Fortran in '57. It was not the first automatic programming language, but it was far and away the most successful, partly because the algebraic nature really spoke to what the scientific community already knew, and partly because he understood that the challenge with any compiler was going to be, can you produce fast code? The hand code is going to be faster than any compiler-generated code. No, Backus told his team on the first compiler, your compiler has to produce object code that is faster than the good hand code. That's hard, but they did. And so that very first Fortran compiler produced better object code for production than competent hand codes. Now, people ask the question of when are we going to see a big jump in software productivity by programmers? The answer is this was the big jump, and we've never seen one like it since. I calculate that it
여기는 아이솔레이션
improvement
왜 상관이
about fivefold on
여기 없으면은
one per programmer per day. And we've never seen a fivefold improvement in anything since that. The other machine I want to remark on is the IBM's last little vacuum tube machine. It was a drum machine. It was so reliable you could put a job in it overnight and let it run all night while you went home, and you came back in the morning and it was still working properly. Okay. It was also the first machine to sell more than 1,000 copies. They sold 2,000 copies of these, and it's the only machine I know that ever had a book dedicated to it. Don Knuth, a great computer scientist, dedicated one of his books to the IBM 650. And they sold it at 60% to universities, and so it became the standard university computer for many years. And I won't go into the details on the 650. Next, the computer generations are defined not by the conceptual structure, but by the technology in which they're implemented. So the 0th generation was mechanical, the first generation was vacuum tubes, and the second generation was discrete transistors. Philco built the first commercial discrete transistor machine. I think Bill worked on one at Bell Labs in the summer of '53, a transistorized machine. But IBM got there with transistors wholesale, and as a consequence, dominated the market. So it became standard to talk about IBM and the Seven Dwarfs as the computer producing companies. IBM had more than 80% of the market. And IBM's first transistor machine was going to be the Stretch supercomputer, and I'm going to talk about it in a minute. But to meet a air defense problem, they rushed together a 709 a 7090 with transistors in 6 months from start to finish. The reason they did it was to take the logical equations from the vacuum tube 709 unchanged, to take the programming manual from the 709 unchanged, and only re-implement it in transistors. And they had the transistor technology that had been developed for the Stretch supercomputer. So that team did a phenomenal job of start to finish, 6 months, delivered the first machines to the Air Force. It was 5 times the 709 in performance, and it cost about $3 million a piece, and hundreds were installed. It became the standard scientific computer. Meanwhile, a team in the West Coast laboratory had developed a little business computer whose principal characteristic was that it had a blazing fast printer. It turned out that for the same rental price, you could take 3 of your punch card printers out of your installation and put in a 1401. It would do as much work and it cost less money, and you could start to program it. And so that snuck the programming nose into the data processing tent, as it were, and people learned that you could do little things on this machine even though you had bought it just as a printer. It was the first machine to sell more than 10,000 copies, and they sold and installed something like 20,000 of these. Meanwhile, back at the ranch, scientific computing's needs was great, and the 7090 was the engineering computer, but for the big scientific jobs like atomic energy or weather prediction, where you ran 40-hour runs routinely. It became important to try to build high-performance machines that would do that. So Univac tried one. It wasn't very successful. IBM undertook to build the Stretch supercomputer, and I was one of the architects on this, and Nancy worked on the transistor circuits for it. It was the market has always been a niche market. If you sold 100 of supercomputers, you were doing well. And so most of the cost is in development cost, not in manufacturing cost. Stretch, we sold 9. We sold them for $10 million a piece. The Stretch was a transistorized machine, stood about 15 feet long, about 5 feet high, about 5 feet deep. But the other characteristic of supercomputers is they have always been the trailblazers for new ideas in architecture and in implementation, and in that case, in the transistor technology. So the Stretch supercomputer 61 used transistor circuits. It introduced an 8-bit byte. It was the first machine to have supervisory facilities so that an operating system, rather than a console operator, controlled the machine. And what does it take? It takes memory protection to separate the instructions and the data and to separate different people's instructions from each other. It requires an interruption capability. One of the early Cray scientific computers didn't have this, and when I saw it installed at Princeton, the operator decided when an endless loop was running and stopped the machine. All right. So it needs a clock, and it needs a privileged operation so you can control what the protection mechanisms are doing. The Stretch was also the first machine to include instruction pipelining. John Cock and Harwood Kolsky came up with that. And Werner Buchholz came up with the standard I/O channel, so that the channel, you could plug any different device into the channel, and you didn't have to have a different kind of channel for a tape and for a disc and for a card reader and for a printer. It was advertised as going to be 100 times the 704. In practice, we couldn't do that. The instructions will make it 100 times the 704, however much it costs, and we did the however much it costs, but we did not succeed in making it 100 times the 704. So they cut the original price from $13 million to $10 million, and then the Justice Department said you can't sell it for that because it costs you more than that to make it, so we had to stop selling them at $9 million. I want to point out now, because I want to talk about people, John Cock was the other universal genius in my experience in the computer field. John was from Charlotte. His daddy was head of Duke Power Company. He got his PhD at Duke, and he was crazy about computers. He talked about computers all the time. I've tried to drive out of the parking lot with John hanging in the window of my car with a new idea. I shared an office with John for a year, and that only worked because he worked at night and I worked in the daytime. And when he was dying, I visited him in his home in Bedford. He was in a wheelchair and in his gown, and he was talking about computers and new technology. His contributions range far and wide. Instruction pipelining, a key concept in computer engineering. Global compilation. He and Fran Allen did that. He and Harwood Kolsky did the pipelining. He built a logical interpreter that simulated circuits, and the 650 program would run faster on the simulator than it ran on the 650 in the later technology. And he invented reduced instruction set computers. And so did David Patterson simultaneously at Berkeley. Both of them had what it took to do that, and that was mastery of both the compiler technologies, which is crucial to instruction set computing, reduced instruction, and the hardware technology. So, and John was a sweetie, and I could tell you tales about that, so could Nancy. So, the other important genius in supercomputers was Seymour Cray. He started with that code-breaking group, ERA. He went to CDC when they split off. Then he founded his own company, Cray. He built his first supercomputer, saying his team consisted of 35 people, including the janitor. And they built an isolated laboratory off in Wisconsin. And he just built computers. I nominated him for the National Academy of Engineering because he didn't have a company to nominate him, and there was nobody. And I never met him, but I knew he needed to be nominated, and he got elected, needless to say. He led the ticket that year, and he declined. He was the only person who had ever declined. And so I wrote him and I asked him why I declined. He said, "I'm not much of a joiner." His philosophy of engineering was build it as fast as possible with the technology you have, regardless of what it costs. And so the machine you see was the Cray 1. It's C-shaped, and people ask, how is the wiring done on the inside? Because it was only 18 inches on the inside to minimize the backplane wiring, make it as fast as possible. He said, one tall girl and one short girl. So the soldering, he needed them real thin and real tall or real short to connect the wires in there, because he was determined that they be short. He said the key to supercomputers is refrigeration, and that was an important concept. Getting the heat out is still today in chips a major problem. He was very successful. Cray 1, Cray 2, Cray, they went on and on. He was unfortunately killed by a drunk driver early in his career, and we miss a lot. Here's what supercomputer looks like today. The world's fastest one is at Oak Ridge, and you can see the specifications. Well, you can't see the specifications on this slide. It was the world's, this is not the right slide, sorry, wrong slide. But today's is something like 4 million processors, 2 million of them, I beg your pardon, 40 million processors. No, 4 million processors, 2 million GPUs, 2 million CPUs, and it was installed just this year. It was put together. It uses Intel CPUs, and it was put together IBM. Now I want to tell you about the 360 experience. It's called IBM's $3 billion gamble. The reason IBM had to do something was we were out of address bits. We were out of address bits in each of the 6 product lines, and memories were getting cheaper, and memories, the universal elixir for system solutions, and so everybody needed more memory. And so we also had 6 product lines competing with each other. And so we had a semi-integrated circuit solution coming, but not until 1965. So Fortune said this gamble was the most crucial and pretentious as well as the riskiest business judgment of recent times. And we'll talk about it a little bit. The first, I'm going to talk about 3 product fights, and I'll try to give you an understanding of what product development is really like. A product fight is not necessarily not cordial. It is a set of differing professional opinions about which way is the best way forward. They may be expressed with each other with great courtesy, and ours were, but they are still strong and strongly articulated professional disagreements. And so the first product fight occurred just inside the big machine division, which encountered this memory addressing problem first. I was working in research, and I was asked to come to Poughkeepsie to be manager of architecture of that division, and told to put together a product plan to address a new product line. So we formulated what was called the 8000 series. It used the transistor technology that we had established. It used the core memory technology we had established. It used an existing running machine that Jerry Blau had designed as the center of the product line, and then a higher speed scientific computer and a lower speed office computer. And in January of '61, we presented this product plan. We had gone through the first round of forecasting, cost estimating, and pricing, which is a cycle one goes through in product development, try to get them to converge. And we presented the product plan. And the key concept was it's going to be cheaper because the technology has gotten cheaper. And one of the problems, if all your machines are out on rent, is how do you maintain your revenue while you're making machines much cheaper? And the answer was you got to develop a new market. And by attaching communications lines, which had not been done in number, and building the whole concept around connecting terminals and communications, we saw a new market. So it looked like we could have had a going plan. At the end of the day, everybody in the room was happy except one fellow sitting way up in the back, who was Van Leersen, the executive vice president. And that night, my boss got shot out from over me and transferred to the Boondocks, and a new boss was brought in from the lower machine division, and that was Bob Evans, and he was told by Leersen, if this plan is right, make it happen. If it's wrong, change it. And so Bob studied the plan for 2 weeks, and we had long conversations, and he decided it was wrong, had to be changed. I decided it was right and shouldn't be planned. And the really difference was 62 versus 65. The earliest, his proposal plan, we could do anything real, was going to be 65, and the competitors were eating us. And so I thought, we ought to go now. Well, Bob's plan said, well, look, let's make warm-overs of our present, one more round of our present products, even though they address limited, that are faster and for the same money, and hold the market, see if we can hold the market for 3 years. Well, they went to the corporate management committee, and it was a very interesting product fight because everybody lined up allies in the company, and Bob and I were reporting to our grand bosses like this, so I didn't tell him everything I knew, and he didn't tell his boss everything he knew. And he called me one day in February and he said, Fred, I want you to know you got a raise. I was startled. We were going like cats and dogs. And I said, thank you, Bob. He said, I want you to know I had nothing to do with it. It went to the corporate management committee in March, and my side won. And so we went home to proceed. Bob didn't quit. He went back to the corporate management committee in April and had his ducks in a row and won. And so he organized a meeting in May then of the whole Data Systems Division Product Development Laboratory, because all the existing 8,000 projects were dying and all the new warm-over machine projects had to be put in place. Well, I was going back to research. I was disgusted. But I went to his meeting at Saratoga Springs, a week-long meeting, to try to make sure my team landed on their feet in the reorganization, and then I was off to research. To my utter amazement, he had so-and-so in charge of this warm-over machine, so-and-so in charge of this over machine, and so forth. And then he asked me to take the new product line, Family Jewels. You could have knocked me over with a feather. What a big man. What a big man. Well, I wasn't sure I wanted to work for Bob. We've been fighting. And it took me about a month to decide. I went and talked to my grand boss, and he said, I never knew anybody who regretted working for Bob Evans. And he was right. Bob and I became a great team. And that was a wonderful experience. Well, so in December, we formed a corporate-wide committee to new product line, not just for the Data Systems Division, but for the whole corporation, all the divisions, and using the new technology. So the warm-overs would hold the market as best, and we had till 65. That meant we could start planning from scratch. So we put together what is this so-called interdivisional committee, the spread committee report, that said we're going to do one product line instead of 6 for the whole corporation. We're going to go from the smallest thing we make to the supercomputer. We're going to make them across all the company divisions, including the military division and the space division. And we're going to try for up-down binary compatibility. Now, up is easy. Down is not easy. Down requires a lot of architectural stress. And the big saving of money, this will enable us to do one software support package. Not necessarily one operating system, not necessarily one Fortran compiler, because we're going to have different memory sizes and the software has to be customized for that, but strictly compatible. And here are the challenges the spread faced. We're going to do 7 implementations ranging with as much as a 50-to-1 performance range at appropriate price points. Each one has to compete in its own separate market on a price performance basis. And that's a challenge. They have to the machines have to be general purpose, do scientific and business applications equally well. They have to generate new technology is going to enable us to cut costs in half. Well, we've got to generate new market to make the revenue up. Okay, so we've got to find new applications. And then we have to figure out how are we going to convert the customers from the existing machines to our new product line instead of them running off to a competitor. No problem. And Honeywell has come out with a machine that will run 1401 code, our 20,000 machine market. And ours will not run 1401 code. All right. So these are the challenges, and we went forward. I've talked about the big product fight, and I'll talk about the second big product fight. This one happened in 1962 and happened inside the project. So whereas the first one was on company strategy, this one was how are we going to make the new product line? And the real question was, do we use 6-bit bytes or do we use 8-bit bytes? The 6-bit bytes use the existing infrastructure and all the existing I/O devices. The 8-bit bytes are going to cost an extra $100 million to engineer all new tape drives, disks, even card punches, because they print the characters over the top. Okay, so which way do you go? Well, the fight inside the team was half of our 20-person architecture team favored the 6-bit bytes, and the other half favored the 8-bit bytes. Jerry Blau worked for Gene Amdahl, who worked for me, as Gene was an architecture manager. Jerry wrote the manual with his own hands and was really the number 2 architect, and they kind of led 2 groups, factions inside. Both were fine men, both were godly men, both were Christians, and both were firmly disagreed as to which way forward computers ought to be built. All right? And so this is characteristic of the fight. So here are the two architects. One of the characteristics you will notice is that this whole team is young. And as a matter of fact, I heard that after the 360 announcement, Tom Watson called for the pay cards of the principals, and he looked at him and said, "You mean we bet the company on people we don't pay any more than this?" And I got a 40% raise that night. I don't know what the others got. And here were the key engineers who built this. John Fairclough, later Sir John Fairclough, and led the British laboratory that built the first of the 360 models. Pete Fagg led the Poughkeepsie laboratory that built 3 of the 360 models, and he coordinated the input-output work for the whole thing. All right, big fight number 3. The new product line is rushing for announcement. Cost estimating is done, forecasting is done, pricing is done. The data systems division, the salesmen are busy preparing the materials and leaking to customers, and everything's on track. January, before April announcement. Lo and behold, out of the West Coast laboratory comes a 1401 successor, 6 times faster than 1401 and using the new technology. Had been developed under the bench for 2 years, okay? And here comes the head of that division, the president of that division, to say, here's a better product plan. You don't want to bet the whole company on one untried product. You've got this 20,000 machine market there. It is extremely profitable because you've had them out a good while and the manufacturing costs have gone down. And it's 2/3 of all the machines IBM sells are 1401s. So why don't you just let the 1401 cover the bottom of the market and you do the new product line for the middle and up. Now, we'll need all the circuits for a while to build the 1401 successor. Fiercely fought. Fiercely fought. Why? As in each product fight case, there are 2 strong, valid cases to be made. Neither one is feeble-minded. They are of fundamental strategic importance. Who decides? Tom Watson decides, the CEO. And he made the gamble saying we're going to go with one. But a key thing that happened the night before that decision was a group with Bill Wright, Bill Hempf at Endicott, Jerry Ottaway, had been working away at figuring out how can we take this microprogrammed Model 30 and emulate a 1401 on it. And before the night was over, and they worked all night, they had shown that the emulator would run 4 times faster than a 1401. It would cost the same as the 1401X would, and it would run new product line code, and you could just switch it to run 1401 code. So you could start with all your existing programs running and move them one by one. So I flew happily back from Endicott to Poughkeepsie that morning, to White Plains, where the meeting, the second day of the meeting was going on, announced this result. That was a stunner. And next day of the meeting, I noticed that the head of the general products division not come. He sent his lieutenant. He knew something had happened in the night, and we had won. And it was Tom Watson had made that decision. Now, Watson was a worthwhile person to know. He had in charge. He took care of people. He really cared about people. And vendors, customers, employees, all had to be treated right. I was leaving IBM. He invited me down to Armonk for a one-on-one lunch in the executive dining room, and you know what that is. That's an arm twisting session. And he tried to persuade me that I didn't want to come to Carolina after all. And he asked me why I didn't, and I explained that I really wanted to get back to closer to the people, and I like to teach, and I felt called to do this. And I said, and I like to build things. And he said, I like to build things too. Have you looked at Poughkeepsie recently? I suddenly realized this 10,000 person laboratory factory complex was his personal creation. He had gotten the company into the computer business. And I never would have thought on that scale of, I like to build things too. Have you looked at Poughkeepsie recently? Well, the other thing he said to me was, you're the only person in the company who's managed both a big hardware project and a big software project, because I later spent the last 2 years working on OS 360 after the machines got released into the factory. And he said, can you tell me what the difference is? And I didn't say, sir, that's above my pay grade. But I said essentially that. I said, that's too hard. I'll have to go home and think about that. And so I thought about that for 5 years, and the mythical man is the outcome from that thinking. Well, here's what happened on the 360. We announced 144 new products on April the 7th. There were 5 processors announced then and some more later. They were originally 25-to-1 performance. By 71, they were up to 200-to-1 performance range from biggest to smallest and upwards and downward compatible. On announcement day, the data salesmen sold twice their annual quota. Oh. The customers had been leaked and primed, and they were ready, and they placed paper orders that day. We had big software problems building. Nobody had ever tried to build an operating system, much less we had not the operating system and 16 different compilers in different languages at different memory sizes. So we called it the peach in the bowl of cherries. But the operating system was very difficult, and it was late and it was slow to start with. There were lots of customer savings, and one of the effects of our architecture is that everybody copied it, and including the Soviets, and the Japanese. So, talked about the product sites. Here are the lessons from the product sites. They involve strategic decisions of great importance. Personalities matter a lot. But the fights are not personal. They are professional, but not personal. They can be courteous. And like Bob calling me about this raise, all right? Courteous, And that's really how it is in product development. And the results, the architecture, the compatibility, the 8-bit byte, as you know, made possible personal computers and made the data processing application. Microcoded implementations are widely used. They're not the best way to do it, and we introduced the concept of emulators for early computers. That was first done by an emulator on the Model 65 for the 7090, as a matter of fact, but then carried over to the emulator for the 1401. And in 1965, I predicted our architecture would last 25 years. The most recent model was announced this year. It has 25% of the world's banking, credit card applications, and essentially we changed the world. Now, if y'all got the patience, I'll go on shortly to tell what has happened yesterday. There became then a mini-computer revolution. Transistors got cheap, and machines could be bought for $25,000 instead of $250,000. And it changed the sociology, because now you could have a department in your machine, and you could control how it was used. And this meant they were originally designed to attach to scientific instruments. And at universities, this was important Because universities had the rule, you got to use the central computer to help pay for it. But yes, you can have an instrument controller in your department. Behold, all right. And so these $25,000 machines. Now, an important lesson is all the existing mainframe manufacturers missed the mini-computer revolution. All. Why? Fat, dumb, and happy. They were very successful doing what they were doing. They were making money hand over fist. And their culture wasn't set up to think that way. Now, along comes the single chip processor. And we have a personal computer revolution. And once again, it's a sociological thing. Instead of being a department computer, it is now a personal computer. And I control what happens to it. And that all the many computer manufacturers missed the personal computer revolution. HP got in late. Digital just died, okay, because they missed the revolution. So once again, watch out for being fat, dumb, and happy. So this summarizes the story. The new technology enables a new price point. The new price point enables new sociologies. The new vendors respond, the established ones don't, and that happened twice. Now, here's the first computer on a chip, 4004, developed by Frederick. Intel was designed originally for a calculator, perhaps even for a watch. And this little chip was equivalent in power to ENIAC's 18,000 vacuum tubes. And it had a 4-bit data path. They moved on the next year to an 8-bit data path. And the story of computers today is that once again there's been an up branch and a down branch. So the ARM processor is the most prominent processor. It's used in 95% of all smartphones. It's a 32-bit machine. And they sold 5 billion of them in 2010. Meanwhile, I'm not going to go here. Meanwhile, the other end of the market is that 4 and 8-bit controllers are still made and used, and in cars there are at least 30 of them, separate of little computers programmed to do all kinds of things, whether you want them to or not. So on that, let me stop and turn you loose. But first I want to say thank you to you for coming. Thank you to the Lord Jesus for the opportunities I've had. I was a half generation behind the pioneers, but I got to meet most of the pioneers and get to know most of the pioneers. I happened to be at the right place at the right time for the 360 project, for the supercomputer. It's just a wonderful life of computing, and all because of given opportunities. So thank you.